Oofs. Look at the car, it's completely rusted. It was a great shot, dude. Cutting wood and melting ice are examples of physical changes. On the other hand, the rusting of iron, burning of wood, and eggs cooked into an omelette are examples of chemical changes. Hey! I will show you something. This is a physical change. Let me burn this. I need some charcoal. Now this is a chemical change.
There are two types of changes, physical and chemical. Physical changes are temporary, and chemical changes are permanent. Substances can undergo either physical or chemical changes to form new substances. In this lesson, you will learn about elements, mixtures, and compounds. At the end of this lesson, you will be able to define physical and chemical changes, identify the types of change given an example, define pure substances and mixtures, list the properties of elements, mixtures, and compounds, and categorize substances into elements, mixtures, and compounds. Have you ever observed an ice cube kept outside the refrigerator for some time?
Ice melts and changes to water.
Yes, there is a change in the state of the ice cube. Now, let's do a small experiment. For this, we need to take 2 beakers with 20 grams of sugar and label them as A and B. Let's add some water to beaker A and stir it. In beaker B, we will add a little sulfuric acid. Now, observe what happens in beaker A. The sugar gets dissolved in water. In beaker B, sugar reacts with sulfuric acid and black sugar charcoal is formed. From this, we can say that the change that has taken place in beaker A is a physical change, whereas the change that has taken place in beaker B is a chemical change. In beaker A, we can get back the sugar by the evaporation of water. On the other hand, in beaker B, we cannot get back the sugar from the carbon. From this observation, we can conclude that there are two types of changes: physical change and chemical change.
How do we define a physical and a chemical change?
After observing the experiment, we can define a physical change as a temporary change in which the composition of the substance remains same and no new substance is formed, but only a change of state occurs. Melting of ice, breaking of glass, tearing of paper, cutting of wood, and changing of water to water vapor are examples of physical change. Likewise, we can define a chemical change as a permanent change in which a new substance is formed that has properties which are different from the original substance. For example, formation of water from hydrogen and oxygen atoms, rusting of iron, burning of wood, lighting of firecrackers, burning of a matchstick. You might have observed the word pure written on the packing of consumables like milk, mineral water, fruit juice, etc. What does the word pure mean to you?
It means having no adulteration.
That's right, but for a chemist, none of these substances are pure. For example, milk is a mixture of water, fat, and proteins. Mineral water, according to the label, has calcium chloride, magnesium sulfate, and sodium sulfate. If it were really pure water, In the scientific meaning of the word, it should contain only water molecules. For a chemist, the purity of a substance means the substance is made up of only one type of a particle. The particles may be atoms or molecules. For example, the element iron is made of only one kind of a particle called iron atoms. So iron is a pure substance. From this, we can define a pure substance as a substance which is made of only one kind of a particle. For example, iron, aluminium, silver, and gold.
Okay. So, the substances that are opposite to pure are mixtures?
For a chemist, when a substance contains more than one type of a particle, it is known as a mixture. For example, salt solution is made up of two components, salt and water. Therefore, salt solution is a mixture.
There are over 100 known elements on Earth.
A pure substance which is made up of only one kind of atom and cannot be broken into two or more simpler substances by physical or chemical means is referred to as an element. For example, iron, gold, and silver.
How does one identify the elements? Do they have any typical properties?
Yes, they do have typical properties. Let's look at some of the characteristics of elements. An element is homogeneous in nature. It is a pure substance, made up of only one kind of atom. For example, iron and silver are made of only iron and silver atoms. An element cannot be broken down into simpler substances by any physical or chemical methods, such as heat, light, electricity, or chemical reactions with other substances. For example, if you were to smash a piece of iron into small pieces or heat it, the piece still remains as the element iron. An atom is the smallest unit that shows all the properties of an element. For example, an atom of iron shows all the properties of that metal. Elements have sharp melting and boiling points. For example, aluminium has a boiling point of 2447 degrees centigrade. Elements can be classified into three classes: metals, non-metals, and metalloids.
Hey! Chocolates!
Did you observe they were wrapped in aluminium foil? Not only chocolates, but biscuits and medicines are wrapped in aluminium foil. This aluminium is a metal. Over 80% of known elements are metals. Let's see what metals are and their properties. Metals are the elements which readily lose electrons to form positive ions or cations. For example, sodium, an alkali metal, loses an electron and forms positively charged sodium ion. Let's observe some of the properties of metals. Metals have luster. When freshly cut, they show metallic luster. For example, gold. Metals are good conductors of heat and electricity. As metals have free electrons in them, they are able to conduct heat and electricity. For example, copper. Metals are malleable, meaning they can be hammered into thin sheets. For example, aluminium. Metals are ductile, which means they can be drawn into wires. For example, copper. Metals are sonorous. They give a ringing sound when they are hit by a hard iron rod. For example, copper. Almost all metals are solids except mercury, which is a liquid at room temperature.
Is sodium chloride a metal?
No, it's not. Let me tell you about nonmetals. They are the elements which readily gain electrons to form negative ions or anions. For example, chlorine accepts electrons from a metal like sodium and forms a negatively charged chloride anion.
Like metals, do nonmetals also have properties?
Yes, of course. Let's look at some of the properties of nonmetals. Nonmetals usually show some or all of the following properties. They do not exhibit luster. Nonmetals are bad conductors of heat and electricity. They do not contain free electrons in them, so they do not conduct heat and electricity. For example, sulfur. They are not malleable. They cannot be drawn into sheets. For example, sulfur and phosphorus. Nonmetals are non-ductile. They cannot be drawn into wires. For example, phosphorus. They are not sonorous. When hit by any hard substance, they do not produce any sound. For example, carbon. Nonmetals exist in all the three states. Thus, 11 nonmetals are gases. Only bromine is a liquid, and the others are solids. The elements which have intermediate properties between those of metals and nonmetals are called metalloids. They are amphoteric in nature. Metalloids react both with acids and bases. For example, boron, silicon, and germanium.
Are water and carbon dioxide gases, not mixtures?
No.
Why? If we take the example of water, it is made up of two kinds of atoms.
Yes, you are right. Water is made up of oxygen and hydrogen atoms, but still, it is a pure substance.
How?
Water and carbon dioxide are examples of compounds.
Compounds? Another set of substances.
No, not quite. A compound is a pure substance that is composed of two or more elements, chemically combined in definite proportion by weight. For example, water is made up of 2 atoms of hydrogen and 1 atom of oxygen. These atoms combine to form a compound known as water. The smallest particle of water is called a molecule. A molecule is the smallest particle of a compound that still has all the properties of a compound. Water, ammonia, carbon dioxide, and limestone are examples of compounds.
Is salt solution a compound?
No, it is not. Even compounds have similar properties like that of elements. Compounds are composed of 2 or more elements which are chemically bound with one another in fixed proportions. Let's look at some of the characteristics of compounds. A pure chemical compound is homogeneous in nature, made up of the same type of molecules. For example, water contains only molecules of water. A compound can be broken into its constituents. For example, water can be broken into constituent elements, hydrogen and oxygen, by the process of electrolysis. A compound has a fixed composition. For example, a water molecule is always composed of 2 hydrogen atoms and 1 oxygen atom. A compound has a distinct set of properties which is not similar with the properties of its constituent elements. For example, sodium chloride, table salt, is a harmless substance which is a white crystalline solid. On the other hand, its constituents, sodium, is a greyish-white solid, and chlorine is a greenish-yellow gas that are potentially dangerous. Sodium is a highly reactive metal which catches fire when exposed to air, and chlorine is highly poisonous. From this we can say that compounds exhibit a distinct set of properties. A compound has a sharp melting and boiling point. For example, water has a boiling point of 100 degrees centigrade and a melting point of 0 degrees centigrade.
Hey, what about vegetable salad? I like it. It's so colorful. Is it a mixture?
Yes, you're right. Observe carefully. The salad contains a variety of vegetables like carrot, cucumber, beetroot, tomato, cabbage, and onion. You can segregate each of the vegetables from one another, isn't it?
Yes. So, vegetable salad is a mixture.
A mixture is matter that consists of two or more substances which may be elements, compounds, or both mixed together physically in any proportion, but not chemically combined. For example, air is a mixture of gases like oxygen, nitrogen, carbon dioxide, etc. These gases are not chemically combined with one another and can be separated by suitable means. Based on the distribution of the particles in the mixture, there are two types of mixtures, heterogeneous and homogeneous mixture. A mixture that is not uniform throughout is called a heterogeneous mixture. For example, a mixture of sugar and salt is a heterogeneous mixture because the sugar and salt particles can be segregated based on their color and size. Examples of heterogeneous mixtures are iron fillings and sulfur powder, concrete, which is a mixture of cement, water, sand, etc. The second type of mixture is a homogeneous mixture. Observe the solution. This is a solution of salt in water. How does this salt solution appear to you? It looks uniform throughout. So, such a type of mixture is known as a homogeneous mixture. Brass, a mixture of copper and zinc. Salt solution, a mixture of salt in water, and a solution of alcohol in water are examples of homogeneous mixtures. Now, let's observe some of the properties of a mixture. There is no definite proportion in which the constituents of a mixture combine. For example, the mixture of salt and sand can be in any ratio. The parts of a mixture can be separated by physical means. For example, a mixture of iron filings and sulfur can be separated by using a magnet. When a magnet is placed in the above mixture of iron filings and sulfur, the iron particles are attracted by the magnet, while sulfur particles remain unattracted. When a mixture is created, no new substance is formed. Each part of a mixture retains its own properties. For example, we could mix various proportions of hydrogen and oxygen gas. As long as you do not ignite the mixture, the combination will form a mixture that can be separated. Energy is neither given out nor absorbed in the preparation of a mixture. For example, no heat or light energy is liberated or absorbed when iron filings and sulfur are mixed together. A mixture does not have a sharp melting or boiling point. For example, sugar solution does not boil at a fixed temperature.
Hi, my name is Buddy. I'm training to be a magician. I practice all day, but I do not seem to be getting things right. Let me try taking a rabbit out of my cap. Abracadabra. Abracadabra. Sorry. Okay. Let me try doing something simpler. Here's a spoonful of sugar and a glass of water. I'm going to make the sugar disappear. Hocus pocus. See? Let me try making the spoonful of chalk disappear in this beaker of water. Hocus pocus. Oops! The chalk is still there. What did I do wrong?
This lesson is all about types of mixtures. By the end of this lesson, you will be able to identify the types of solutions, list the properties of a solution, define concentration, differentiate between saturated and unsaturated solutions, list the properties of a suspension, list the properties of a colloid, and differentiate between solutions, suspensions, and colloids. Take 3 beakers with 50 milliliters of water in each. Add a spatula of sugar crystals to beaker A, a spatula of powdered chalk to beaker B, and a few drops of milk to beaker C. Stir well with a glass rod. Particles can be seen in beaker B, but not in A or C. Direct a beam of light from a torch through the beakers A, B, and C, and observe each beaker from the front. The path of light is visible in case of B and C, but not in A. Leave the mixtures undisturbed for some time. Now, filter each of the mixtures. You will find a residue on the filter paper for beaker B. The mixtures in the beakers are of 3 distinct types. The mixture in A is a solution, in B is a suspension, and in C is a colloid.
Hey! I could use this while performing tricks. Tell me more. I'm thirsty. Let me conjure up a bottle of cola for myself. Is this cola a solution as well?
That's right. Aerated drinks are nothing but gases in a liquid solution. A solution is a homogeneous mixture of 2 or more substances, which means that the density, viscosity, and other physical properties are the same in any part of the solution. For example, a salt solution tastes the same throughout. A solution has a solvent and a solute as its components. A component of the solution that is present in a larger amount is called the solvent. A component of the solution that is relatively present in a smaller quantity is called the solute. A solution of iodine in alcohol is known as a tincture of iodine. The iodine is the solute and alcohol is the solvent. This is an example of a solid in a liquid solution. An aerated drink is a gas in liquid solution, where carbon dioxide is the solute and water is the solvent. Air is a homogeneous mixture of a number of gases. It is an example of a gas in gas mixture.
Now watch as I make this cola disappear.
A solution is a homogeneous mixture of 2 or more substances. The particles of a solution are smaller than 1 nanometer in diameter, so they cannot be seen with the naked eye. When you direct a beam of light through the solution, it is not visible. Since the particles in a solution are very small, they do not scatter a beam of light passing through the solution. The solute particles cannot be separated from the mixture by filtration. Since the particles are very small, they pass through filter paper. When a solution is stable, it means that the solute particles do not settle down at the bottom of the container even if you leave the solution undisturbed for a while.
I found this bottle of concentrated magic potion among my teacher's things. I'll have a few sips and turn into a powerful magician. It tastes terrible. I hope it works. Let me try making the flowers grow bigger. I think the potion was too dilute.
Concentration is defined as the amount of solute present in the unit volume of a solution. A solution that contains a relatively smaller quantity of solute as compared to the solvent is known as a dilute solution. The concentration of a solution can be expressed using two methods. Mass by mass percentage of a solution is equal to mass of solute divided by mass of solution multiplied by 100. Mass by volume percentage of a solution is equal to mass of solute divided by volume of solution multiplied by 100. Now that you know what mass by mass percentage and mass by volume percentage of a solution means, let's look at situations where these concepts can be applied. A solution contains 20 grams of sodium carbonate in 240 grams of water. You need to calculate the weight percentage of the solution. In the given problem, the weight of the solute, sodium carbonate, is 20 grams. The weight of the solvent, that is water, is 240 grams. We know that the weight of the solution is the sum of the weights of the solute and the solvent. Let's use this formula to solve the problem. The weight of the solute is 20 grams and the weight of the solvent is 240 grams. Therefore, the weight of the solution is equal to 260 grams. We know that weight percentage is equal to the weight of the solute divided by the weight of the solution multiplied by 100. Therefore, we substitute the values of the weights of the solute and the solution in the formula. Hence, the weight percentage of the solution is 8.33%. Let's try out another example. 15 milliliters of hexane is mixed with 45 milliliters of benzene. You want to calculate the volume percentage of the solution. In this problem, the volume of the solute, hexane, is 15 milliliters and the volume of the solvent, benzene, is 45 milliliters. The total volume of the solution is equal to the sum of the volumes of the solute and the solvent. The volume of the solute is 15 milliliters and the volume of the solvent is 45 milliliters. Adding both the volumes, you get the total volume of the solution equal to 60 milliliters. We know that the volume percentage is equal to the volume of the solute divided by the volume of the solution multiplied by 100. Therefore, the volume percentage of the solution is given by dividing 15 milliliters by the total volume of the solution, that is 60, into 100. Hence, the volume percentage of the solution is 25%.
This is fun and so simple. Let me add more salt. I must have messed up again. The salt is not dissolving anymore.
Even if you stir the solution vigorously or wait for a long time, the solution will remain undissolved. You have obtained a saturated solution in which no more solute will dissolve. The solution that we had obtained initially was an unsaturated solution. Now heat the saturated solution. The undissolved solute present in the saturated solution slowly dissolves as the temperature rises. after the solute has dissolved completely, slowly cool the resultant solution to room temperature without disturbing it. The solute, which was undissolved before heating, has now dissolved. This means that the solute dissolved in the present solution is more than its solubility. The type of solution that we just discussed is called a supersaturated solution. In this solution, the solute present is more than in the saturated solution. Even a slight disturbance will make the solute precipitate out, and you will be left with a saturated solution. Therefore, we can classify a solution as saturated, unsaturated, or supersaturated, depending on the amount of solute present in the solution. Solubility can be defined as the maximum amount of solute by weight in grams dissolved in 100 grams of solvent at constant temperature. For instance, at 20 degrees centigrade, a maximum of 36 grams of common salt can be dissolved in 100 grams of water. So the solubility of common salt is 36 grams at 20 degrees centigrade. A suspension is a heterogeneous mixture in which the solute particles do not dissolve and remain suspended throughout the solvent. The solute particles can be seen with the naked eye.
Aha! So that's why when I added chalk powder to the beaker of water, it didn't dissolve.
Exactly. A mixture of chalk powder and water is an example of a suspension. Other examples of suspensions include milk of magnesia, sand in water, and flour in water. A suspension is a heterogeneous mixture. The particles of a suspension are quite large, and they scatter a beam of light passing through the suspension and makes its path visible. A suspension is unstable. When a suspension is left undisturbed, its solute particles settle down at the bottom of the container. The solute in a suspension can be separated from the mixture by the process of filtration.
Let me try a new trick. I'll put some ink into this glass of water. Then I'll pass a ray of light through the glass. I've become a magician at last.
A mixture of ink and water is an example of a colloid. Since its particles are smaller in size than those of a suspension, a colloid seems to be homogeneous. However, a colloid is actually a heterogeneous mixture. The particles of a colloid are very small and cannot be seen with the naked eye. The particles in a colloid do not settle down when left undisturbed. This shows the stable nature of the colloid. Colloids can scatter a beam of light and make its path visible. Particles in a colloid cannot be separated from the mixture by the process of filtration. A colloidal solution has two components, the dispersed phase and the dispersing medium. The solute-like component or the dispersed particles in a colloid form the dispersed phase. The component in which the dispersed phase is suspended is known as the dispersing medium. You can classify a colloid according to the state of the dispersing medium and the dispersed phase. There can be many types of colloids. The table shows you examples of colloids based on their dispersed phase, dispersing medium, and type. An aerosol is a colloid in which the dispersed phase is a solid or liquid and the dispersing medium is a gas. Smoke and automobile exhausts are aerosols in which solid carbon particles are dispersed in air. Fog, clouds, and mist are aerosols in which water is dispersed in air. Foam is a colloid in which a gas is the dispersed phase and a liquid is the dispersing medium. Shaving cream is an example of foam in which air is dispersed in water or alcohol. Solid foam is a colloid in which a gas is the dispersed phase and a solid is the dispersing medium. Foam rubber, sponge, and pumice stone are examples of solid foam. In foam rubber, the dispersed phase is air and the dispersing medium is rubber. An emulsion is a colloidal system in which both the dispersed phase and the dispersing medium are liquids. The liquid which is the dispersed phase is not miscible with the liquid that is the dispersing medium. Milk is an emulsion in which the dispersed phase is liquid fat and the dispersing medium is water. Face cream and cod liver oil are other examples of emulsions. A sol is a colloidal system in which a solid is the dispersed phase and a liquid is the dispersing medium. Starch solution is a sol in which starch is the dispersed phase and water is the dispersing medium. Other examples of sols are gold sol, milk of magnesia, and mud. A solid sol is a colloid in which both the dispersed phase and the dispersing medium are solids. Ruby glass is a solid sol in which gold is dispersed in glass. A gel is a colloidal system that contains a liquid as the dispersed phase and a solid as the dispersing medium. Jelly is a colloid of water dispersed in gelatin. Curd, cheese, and butter are all gels. When a fine beam of light has passed through a colloidal solution placed in a dark place, then the path of the beam gets illuminated. The illuminated path of the beam is called the Tyndall cone. This phenomenon of the scattering of light is called the Tyndall effect. The Tyndall effect can also be observed when a fine beam of light enters a room through a small hole. This happens due to the scattering of light by the particles of dust and smoke in the air. When sunlight passes through the canopy of trees in a forest, you can see the Tyndall effect at work again. In the forest, mist contains tiny droplets of water, which act as particles of colloid dispersed in air. In solutions, the particle size is 10 angstroms. In colloids, the particle size ranges from 10 angstroms to 2000 angstroms, while the particle size is greater than 2000 angstroms in suspensions. The particles are invisible in solutions, while the particles are visible in colloids and suspensions. Particles in solutions and colloids pass through filter paper easily, while the particles in suspensions do not pass through filter paper easily. The Tyndall effect is not observed in solutions and suspensions, while it can be seen in colloids. A solution is a homogeneous mixture, while both suspensions and colloids are heterogeneous mixtures.
Hi. My name is Blob. I'm just about to make a cup of coffee for myself while we chat. Oops. I must have added salt instead of sugar. Let me try to remove the salt from the cup. Now, I'm in a mess. I wonder how you separate a solid from a liquid, or even a liquid from a mixture of liquids. Any ideas?
This lesson is about the different methods that can be used for separating the components of a mixture. By the end of this lesson, you will be able to identify the most appropriate method of separation of a given mixture using magnets, evaporation, filtration, centrifugation, a separating funnel, sublimation, chromatography, distillation, and crystallization. You may come across several types of mixtures in daily life as well as in the laboratory. Mixtures can be classified on the basis of their physical states. Solid, solid mixture. Metal alloys are actually solutions of solids in solids. For example, brass is a solution of zinc in copper. Solid, liquid mixture. A sugar or salt solution is an example of a solution of solid in a liquid. Liquid, liquid mixture. Alcohol in water is a liquid in liquid mixture. Liquid, gas mixture. For example, carbon dioxide mixed in water. Gas, gas mixture. Air forms a gas in gas mixture as it is a solution of gases like oxygen, argon, nitrogen, and carbon dioxide. If you are provided with a sample of a mixture and asked to separate the constituents, you first need to figure out the type of the mixture.
Hey, that's so cool. Though I don't know why this happened.
You can separate a mixture of sulfur and iron filings by passing a magnet over it. The iron filings will get attracted to the magnet and will stick to it. You can use this method to separate a mixture in which one of the components is a magnetic material.
Now I get it. I've been trying to remove the salt from this solution, but it doesn't seem to be working.
You can separate salt from a solution by evaporating the water from the solution. Evaporation is the process in which a dissolved solid substance is obtained from a solution by allowing the solvent to vaporize. Let's take a look at this process through a demonstration. Take a common salt solution, put it in a china dish and heat it gently. You will observe that the water evaporates and the common salt is left behind in the china dish as a white solid. Evaporation is used to separate a mixture containing a non-volatile, soluble solid from its volatile, liquid solvent.
Oh no! I forgot to use a strainer. Now I've got tea leaves floating inside my teacup.
Using a strainer to strain tea leaves is very similar to the process of filtration. Filtration is a process by which insoluble solids can be removed from a liquid by using a filter paper. A filter paper is a special type of paper which has pores that are tiny enough to let only liquids pass through it. If you pass a solution through filter paper, any undissolved solid particles will get left behind on the paper, whereas the liquid will filter through. The liquid that passes through is called the filtrate, and the undissolved solid particles are called residue. Imagine you want to separate a mixture of chalk powder and water. For separating this mixture, first take a round strip of filter paper, fold it into half, then into a quarter, then open it in the form of a cone and place it in a funnel. Fix the filter paper to the funnel using a few drops of water. Now pour out the mixture slowly with the help of a glass rod. The filtrate collects in the beaker and the residue is left behind on the filter paper.
I am trying to turn this cream to make butter. I'm really tired. I wonder if I could get butter by just filtering the cream.
The particles of fat in the cream cannot be separated into butter simply by filtering the cream. The fat particles are too small and will pass through a filter paper. You can separate such mixtures of solids and liquids by the process of centrifugation. The principle is that when the liquid is spun rapidly, the denser particles are forced to the bottom and the lighter particles stay at the top. Centrifugation is used for blood and urine testing in diagnostic laboratories, in dairies to separate butter from cream, and in washing machines to squeeze out water from clothes.
I accidentally poured oil into this glass of water. How do I separate the oil from the water?
When two liquids do not mix, they form two separate layers and are known as immiscible liquids. These two liquids can be separated by using a separating funnel. A separating funnel is a special type of glass funnel, which has a stopcock in its stem to regulate the flow of liquid. To separate a mixture of oil and water, follow these steps. Pour the mixture into the separating funnel with the tap closed. Let the mixture stand undisturbed for some time. Two layers separate out. Oil being lighter forms the top layer and water forms the lower layer. Remove the stopper and open the tap to run the water layer into a beaker. You will be left behind with just the upper layer of oil. In fact, the same method of separation is used to extract iron from its ore. The slag and molten iron form two distinct layers inside the furnace. The lighter layer of slag is removed from the top and the molten iron gets left behind.
Great idea. My teacher asked me to separate sodium chloride from this mixture of sodium chloride and ammonium chloride. Someone please help me.
Ammonium chloride changes directly from the solid to the gaseous state on heating. This is known as sublimation. So, to separate a mixture that contains a salt and a sublimable solid, such as ammonium chloride, you can use the process of sublimation. Take the mixture in a china dish and cover it with an inverted funnel fitted with a cotton plug. Heat the mixture. In a short while, you will see vapors of ammonium chloride. Stop heating and allow the setup to cool. You will see a fine white powdery deposit on the sides of the funnel. This is solidified ammonium chloride. Solids like camphor, naphthalene, and anthracene are examples of solids that sublimate.
That was easy. First, take a thin, long strip of filter paper. Use a pencil to draw a line on it, about 3 centimeters above the lower edge. Then, put a small drop of black ink on the filter paper in the center of the line, and allow it to dry. Finally, lower the filter paper into a jar containing water, so that the drop of ink on the paper is just above the water level. Don't disturb the jar. You will see that the water rises up the filter paper. But why are there different colored spots on the paper strip?
The ink has water as the solvent, and the dye is soluble in it. As the water rises, it takes the particles of dye along with it. Since a dye is made of 2 or more colors, the color which is the most soluble rises faster and higher. This is why there are differently colored spots on the paper. This process of separation is called chromatography. This method gets its name from the Greek word for color, chroma, as it was first used for separating colors. Chromatography is specifically used to separate a mixture that comprises solutes that dissolve in the same solvent. The technique we have just seen of using paper to separate the components of ink is referred to as paper chromatography. Chromatography is used for separating colors in a dye, pigments from natural colors, and drugs from blood.
I have to separate a mixture of acetone and water. How do I do that?
To separate a mixture of water and acetone that form a miscible liquid pair, set up the apparatus as shown in the diagram. Put the mixture into a distillation flask. A distillation flask is a round-bottomed flask with a tube at its neck. This tube is attached to a Liebig condenser. The Liebig condenser is a long glass tube within a glass jacket with an inlet and outlet for water. The open end of the flask is fitted with a one-holed rubber cork through which a thermometer is introduced. Heat the mixture. You will see that the acetone, which has a lower boiling point, vaporizes first and then condenses in the condenser. It can be collected from the condenser outlet. Water gets left behind in the flask. This process of conversion of a liquid into vapor by boiling and then recondensing the vapor into liquid is called distillation. This method is used for the separation of a mixture containing two miscible liquids that boil without decomposing and have a large difference between their boiling points.
What if the boiling points of both liquids are close to one another?
In case the difference in the boiling points of the liquid is less than 25 Kelvin temperature, you can use the fractional distillation method. Let's take an example of two such liquids, N-hexane and N-heptane. As you can see in the diagram, the apparatus is almost the same as used in distillation. The only difference is that a fractioning column is fitted in between the distillation flask and the condenser. A simple fractioning column is made up of a tube packed with glass beads. The beads provide the surface for the vapors to cool and condense again and again. The fractioning columns obstruct the smooth upward flow of vapors. During this process, only the vapors of N-hexane, which has a lower boiling point, pass through and get condensed in the condenser. N-heptane, which has a higher boiling point, condenses and flows back into the distillation flask.
Phew! That sounds complicated.
Not really. Let's try to understand the process. Air is made up of different gases like nitrogen, oxygen, and carbon dioxide. These gases are separated from one another by the fractional distillation of liquid air. Here are the steps in this process. Air is compressed in the compressor and cooled in the refrigeration unit. Thus, the air gets liquefied. The liquid air is passed through a filter to remove impurities and then fed into a tall fractional distillation column from near its base. The apparatus is warmed. On warming, liquid nitrogen boils off first to form nitrogen gas, as it has the lowest boiling point of -196 degrees centigrade. This nitrogen gas collects at the top of the fractional distillation column. Liquid argon has a slightly higher boiling point of -186 degrees centigrade, so it boils next. It collects as argon gas in the central part of the fractional distillation column. Liquid oxygen has the highest boiling point of -183 degrees centigrade. It boils last. It collects as oxygen gas at the base of the fractional distillation column. If you want to obtain only oxygen gas from the air, separate out all the other gases and collect just the oxygen gas. The diagram shows you the apparatus that is used for separating oxygen from air. Take a sample of impure copper sulfate in a china dish. Dissolve the copper sulfate using as little water as possible. Filter the copper sulfate solution. Next, evaporate the water from the solution so that you get a saturated solution. Cover the solution with a filter paper and leave it at room temperature to cool for a day. Don't disturb the setup. After a day, you will find crystals of copper sulfate in the dish. This time, the crystals will be pure. This process is called crystallization. It is used to purify solids.
Why can't we just evaporate an impure solution to get a pure solid?
When you heat a sugar solution, for example, the sugar may get charred when you heat it to dryness. On evaporating the solution, the solute may still not be pure as it may contain impurities left over from filtration. This is why crystallization is a better method. Crystallization is used for purification of salt that we get from seawater, and separation of crystals of alum from impure samples.